Welcome, Clara.
Thanks.
Clara Lucie Pollock.
Yes.
Welcome to SDU and welcome to our library reading room.
Thanks.
Actually, research reading room.
Yep.
And the reason why I'm talking English now is that we're going to do this in English. And you're Scottish.
Yeah, from Scotland.
Yeah.
Mm-hmm.
And you're not quite fluent in Danish yet.
Not yet, no.
So
would be a bit of a disaster, I think, if we tried to do this in Danish.
So we'll do it in English.
Yes.
Yeah, I hope that everybody's pleased with that. But so you're from Scotland and you did your master's in Edinburgh
Yes.
recently.
Yeah, so I graduated this summer, 2024.
Yeah.
Yep.
So you're now a PhD student at the Cosmic Dawn Center.
Yes.
At the Niels Bohr Institutet in Copenhagen.
Mm-hmm.
And you started up in September,
yeah, the
right?
start of September.
Yeah,
mm-hmm.
Last year. So fairly recent.
Yeah, I've just been there for a couple of months now.
Yeah.
Yeah.
But and I know that you're going to give a colloquium later today together with Casper Heinz,
mm-hmm.
who's here in the audience with us. So of course I'm going to hear a lot about your stuff, your science there. But for the people who are not attending the colloquium, we're going to talk a little bit about it today here. So what are you up to?
Yes. So I work on high redshift galaxy astronomy. I'm working with data from the James Webb-telescope, mostly spectroscopy. And yeah, since I've started working with Casper, we've been looking at mostly the galaxies above redshift 8, so the very, very beginning, the very first galaxies that formed in the universe.
Yeah.
And looking at something called damped Lyman alpha absorption, to try and calculate how much neutral hydrogen is surrounding and embedded in these galaxies at early times.
Yeah. Because the amount of hydrogen that's there is essential for the evolution of the galaxy.
Yeah, so we think that, well, star formation happens because of the inflow of neutral gas into the galaxies. Yeah. So they're sort of the fuel that creates the first stars.
Yeah.
And we observe higher column densities of hydrogen at these redshifts than at lower redshifts in the universe. Yeah. So we think that might be because of high star formation rate in the early universe that formed these first galaxies.
Yeah. Mm-hmm. So recently, from the Dawn Center was an article in Astronomy and Astrophysics.
Yes.
And there was a press release, I think, last week or something like that. Were you part of that?
I was on that paper, yes. The primal paper. So that was all of the publicly available spectra above redshift 5.5, I think.
Yeah.
And that's about 600 galaxies.
Yeah.
So
that's a lot of galaxies.
It's a lot of galaxies. There are a lot of galaxies in the universe. Creates a lot of interesting work for us to do.
Yeah.
So my work is more of a smaller subset of that. So around 50 galaxies that we have that are above redshift.
Still 8. A lot of galaxies.
Still a lot of galaxies, yeah. But can do a more sort of detailed analysis on the modelling of this damped Lyman alpha wing to try and get the column densities.
Yeah.
Mm-hmm.
Right. So I was thinking. So the main goal of looking at this is to answer some questions. I mean, besides just knowing about the evolution of galaxies and hydrogen and so on. But what are the main questions that you're trying to answer?
Yeah. I guess it's sort of the broad goal would be to understand galaxy formation in general, but also with how the gas in these galaxies scales with the star formation rate, and also how many metals are present that are created in stars, and also the dust that's present. So all of the processes that go towards galaxy formation are super interlinked, and by getting a good handle on the hydrogen, we can sort of understand other processes as well.
Yes, of course, but to the people watching this, so hydrogen, there was plenty of hydrogen from the beginning in the universe. It was created in the Big Bang. But when you say metals, you mean, of course, things that are atoms that are heavier, more complicated than hydrogen.
Yes.
And they are typically formed in stars and spread out in the galaxy or galaxies when they explode and so on.
Mm-hmm.
So of course, there was in the beginning of the universe, there was a lot of hydrogen, some helium, and some other trace elements.
Yeah, I think traces of lithium.
Yeah, so when you say metals, what kind of elements are you really thinking about?
Yeah, that's a good question. I think I have a bad habit of saying metalist too, and non-astronomers might not know that. I mean mostly oxygen, I think. Oxygen, carbon, nitrogen, anything that's heavier than helium essentially is a metal to an astronomer. And oxygen is the second most abundant after hydrogen in the universe, so that's the easiest to measure and the most abundant by mass.
Yeah. So oxygen is, of course, it's not a metal to us, but it's I mean, it's familiar, of course, to us humans here because that's what we breathe, and there's a lot of oxygen in the atmosphere. And when you have at the moment, the solar activity is quite high.
Yes.
We see aurora also, and I think oxygen is one of the atoms that causes these colors that we can see at night. Is it the same kind of colors that appear in the spectra? I mean, is it the same kind of sign of lines, or
the same
highly
wavelength of line?
No?
That's a good question.
No, maybe it's not a fair
question.
Maybe it's not a fair question.
I think I'm used to thinking of things like in the infrared because that's when we observe them. So
it's in the infrared, of course.
Well, because it's been so shifted because the galaxies that we look at are super far away. So
they're super far away, and hence they're moving quite fast.
Moving very fast away from us.
Hence the redshift. Redshift of 5, you say. Yeah. So what does that translate to in terms of years? Where are we in history of formation of galaxies?
With redshift 5, I think, is that around 600 million years after the 1 billion. 1 billion years after the Big Bang.
And then Clara's looking at her supervisor, I can say.
Yes, and so redshift 8 to 10 would be
so still a billion years.
Million years after the Big Bang.
So the first billion years, you're still in that regime. So right. Can I ask you the eternal question? I think maybe in cosmology or astrophysics, what came first, galaxies or stars? I mean, because the galaxies are made up of stars, and sometimes we're talking about, well, did the first stars appear before they started clumping together and make galaxies, or was it really some kind of gravitational potential that first created, and then the stars came in that? I don't know if it's a fair question, but it's at least a long-standing one.
It's an interesting question. I don't think I know exactly, but I would imagine that a gravitational potential would have had to have formed before the stars. So I would think that it would be much easier for stars to form if there was a large gravitational potential, which would then create a galaxy. I don't think a star would have just formed on its own somewhere with nothing else around it.
But I mean, the whole story of stars and generation of stars and the evolution of galaxies, of course, somehow go hand in hand. So when you're talking about star formations, then of course, obviously, stars are formed from previous generations, or
but most of them would have formed in one big clump at the beginning of the galaxy formation. So,
So what do you look forward to be doing in your PhD now? You have almost 3 years. So what do you hope will happen?
That's a big question. I don't know for sure what will happen. I mean, that's a good thing with research, is that you never know what direction it might take you. But we have a really large sample of galaxies. We have something called the Dawn JWST archive. So all of the publicly available photometry and spectra are all on there that have been produced by Gabe Brammer and others at Dawn. So as more data becomes public, then they're all just going to go on the archive, and that's even more data for us to look at.
And it'd be publicly available also? I mean,
yes, well, for anyone, essentially. It doesn't have to be a researcher or at university, or anyone can go on and use that.
Cool. Can I ask you, what is the most interesting thing you've been part of science-wise so far, or the most you think important discovery that happened within your field recently?
I think in general, just being able to use the data from JWST, and I feel like I'm sort of coming into academia at the perfect time where all of this data is available
from
it's
James Webb.
From James Webb, especially, and the resolution is so great with the spectra that we can see like very faint lines, for example, like the certain oxygen lines that are needed to calculate the temperature and the metallicity would have been very, very rare to get any of those at a high redshift before James Webb, and now they're becoming more and more common. So I think just the opportunity to
well, everybody's saying James Webb is fantastic.
Yeah, no, but it really is great. Yeah.
But I mean, you can think of James Webb is a generation thing. Also, there were telescopes before James Webb.
Yes.
Of course, and when they came out, it was fantastic. Then came James Webb. What's next? I mean, what would be, in your mind, the next step after James Webb, if you would imagine some instrument that would be even more fantastic? What would it have to do? Is it a spectral range thing? Is it a resolution thing? Is it a kind of a specific wavelength or?
Yeah, I mean, I guess it would be great to push it even further into the infrared, because then you can see things that are further away. But yeah, you would need to get good resolution for that as well. Otherwise, you're seeing very, very faint objects. I'm not sure how realistic it would be to build an even bigger version of James Webb. I know that James Webb has a sort of integral field unit, which means that you can divide into sort of a grid for some galaxies, and you can look at each little pixel and get a spectrum for each pixel. And that means that you can sort of spatially resolve some things that are happening in the galaxy. So instead of just getting data for the whole thing at once, you can get the pixel. And I think, I'm not sure what redshifts we can get that up to, but it would be really cool to be able to resolve a very redshift 8 galaxy with them. Then you could see which points the star formation would be in.
Well, but until then, I think you have plenty of data.
Yeah.
50 galaxies.
And up to 600, 700 if we put the sample all the way down to redshift 5. So a lot of galaxies to work on.
Well, I look forward to seeing what you find out and to hearing about it. Maybe invite you back when you publish your next paper. Yeah. But it was cool of you to come. I'm glad that we had this talk about galaxies far, far away. And I hope that the viewers here also were inspired. So thank you for coming.
No, it was great.
Bye-bye.